Hello, during this video I'm going to tell you about the even more exciting stellar evolution of massive stars. So these are stars more than 8 times the mass of our Sun. Now what happens with these stars is that their lives are blissfully short. Okay, so as I mentioned beforehand, the more massive a star, the faster it burns. Its lifetime in the main sequence is much shorter. So if it was 10 times the mass of our Sun, it would be 20 times 10 to the 6 years of lifetime on the main sequence. Then what happens? So eventually the hydrogen and helium will run out, but the massive stars, this is painfully quick, and what happens, the star will become colder and redder and start to swell. Obviously this is on a bigger scale now, so rather than just a red giant, we now form red supergiants. If we look in more detail, in 1 week a massive star, and this is the time span, exhausts its core of hydrogen fuel and begins fusing heavier elements. Okay. It produces successively deeper layers at higher and higher temperatures. Okay. So it's much like an onion and working out, so it's trying to collapse in itself, and eventually layers upon layers getting hot enough to allow fusion of heavier elements. Now, silicon fusion happens about 8,000 million Kelvin, and that produces an iron core, and that's the limit of the ideas of nuclear fusion, and that's something which can be recognized that iron has the most stable structure, and that's something we can remember from when we were doing nuclear fusion and nuclear fission a while back. So that's 1 week. At a certain point, there's no more fuel available for fusion at all. So in a fraction of a second, what happens is the gravity takes over and compresses the core and raises its temperature to 10,000 million Kelvin. And as this temperature, nuclei start falling apart, releasing millions of years of energy. And this is a supernova. In this case, a type 2 supernova. I'll explain about the other type of supernova another stage. So what happens is this gravitational potential energy causes this collapse. There's such an intense pressure and heat that the nuclei fall apart, and the huge amount of energy is given out. So the total energy output of such an event is 10 to the 44 joules, or as much energy as the Sun will produce in its whole lifetime. And you can see there a picture in space of a star beforehand, and a star in the supernova, undoubtedly the brightest thing that we will possibly see. Now, with the supernova, the dust and the gas on the outside of the supernova are thrown away by the explosion, and the remaining core turns into a neutron star. Now remember, in my previous session talking about normal stars similar to the mass of our own Sun, then if this core is turned to a neutron star, it must be more than 1.4 times the mass of our own Sun. So what's a neutron star? A neutron star is where protons and free electrons combine to form neutrons and a lot of neutrinos as it happens. Now the iron ore collapses, so what happens is a 12,000 kilometer diameter iron core possibly become compressed into a 20 kilometer diameter neutron star. You've got to really understand the change in density here is huge. Those outer layers, unsupported, so collapse and bounce off the virtually incompressible center of the star, and this is due to something known as electron and neutron degeneracy pressure, and that's because the electrons and the neutrons simply can't possibly be squished anymore. So that means there's no ability to have further compression, so they'll collapse in there and then explode outwards, losing a lot of mass of that star. In fact, it's quite interesting. So the supernova, or the presence of a supernova, can often, this force of energy can actually help the formation of future stars, because it can destabilize giant molecular clouds and cause another generation of stars to create. I really like this little fact here. 1 sugar cube's volume worth of a neutron star has a mass which is equal to the combined mass of all of humanity. Okay, so we're talking seriously dense there. Now, can you see a neutron star? Might be a question you ask. Well, what happens is no. The neutron star is no longer going through a nuclear fusion of any sort, so therefore you can't, but you could spot a pulsar. It's like, what's a pulsar? So what happens is the nuclear central neutron star starts to rotate around, and there's a central axis, this magnetic axis. And what happens along this magnetic axis is, because of the rotations taking place, it emits very high frequency radio signal along this magnetic axis, this radio, and sometimes X-rays as well. And what happens is it rotates around and acts a little bit like a fast rotating lighthouse across space. So as this rotates around, whenever you're in the glare of that axis, then you're likely to get a hit of lots of radio and X-rays, and that can be observed. Okay, not in the visible spectrum, but it's something which can be observed. It's quite interesting because when this situation was first observed, what they saw was an unexplained set of pulses in the radio spectrum. And the first person to observe this is said to have written LGM next to the corner of the observation, thinking this could be little green men communicating through radio waves for the first time. So, exam type questions. Observations with a radio telescope in 1967 detected signals from a mysterious source which was called a pulsar. What type of star is a pulsar? What was unusual about the signals? Okay. And 3, pulsars emit, okay, is one question. Pulsars emit radio waves continuously. Explain why the signals detected on Earth are not continuous. You may be awarded a mark for clarity of your answer. So I know that those two questions kind of answer themselves. They should be seen separately. But let's think about our answers now. So pulsars are a neutron star. Signals are regular pulses at precise intervals, often very short and fast. So if time is given, it should be in the order of seconds. Now what a pulsar is not continuous. The star spins or rotates, and whenever it points at the Earth, the radio beam sweeps and passes the Earth once per revolution, or sometimes twice per revolution. So there's an analogy that should be with a lighthouse, or you could show a diagram here showing a narrow beam passing and shining on planet Earth occasionally. So we've got these things called pulsars. Now we've got another scenario. If the post-supernova core is substantially more massive than, and this is another important limit, the Oppenheimer-Volkoff limit, which is about 2 to 3 solar masses, the electron and neutron degeneracy pressure will not be enough to oppose the gravitational collapse. So that means the gravitational collapse will continue, and the star will become what's known as a black hole. Okay, so this is what we're talking about, that central neutron star. If the mass is greater than 2 to 3 solar masses, then we get something special. And that's obviously a black hole. So let's think about what a black hole is again. A black hole is an object where, if we look at the kinetic energy, and if we think about it equals the gravitational potential energy, we know half mv squared equals gmmr. The mass of the object, which we're talking about, and the mass of the central star. Now this is great because the mass of whatever test device we're using is eliminated in this formula. So therefore, to escape it, you're going to have a velocity which is equal to the square root of the gravitational constant, the mass of the object divided by the radius of the object. Now, Schwarzschild calculated the radius of an object which will require the speed of light as the escape velocity. So if we put the v equals c, that means that anything beyond that and this is the limit, that means light cannot escape. So the Schwarzschild limit is calculated from this, and it's a radius, and depending on the mass, and remember here, the mass here could be any number. Okay, so there could be some very, very small black holes out there, or there could be some very big black holes, and there's lots of interesting questions about that. Question: find the Schwarzschild radius for a black hole of mass 4 times 10 to the 30 kilograms. Remember, gravitational constant is 6.67 times 10 to the minus 8 newtons meters squared per kilogram squared. So use that formula. We know the Schwarzschild radius equals 2 times g times m divided by c squared, and that will give me a radius of 5.9 times 10 to the 6 meters. This would be the event horizon, the point where no light can possibly escape. So the evidence we have here of these black holes existing, because clearly we can't see them, we have gravitational lensing, and this is, we can observe the bending of light from stars. And actually what happens is if there's a distant star, what will happen is, and you can see in the diagram, there's kind of like a circle of light, and that circle of light is an indication that there's a black hole somewhere causing the light to bend around it on either side. We also know that matter falling to the black hole may rub and get really hot. Okay, so that means it emits in the X-ray spectrum. The diagram we can see here is, first of all, much like, I guess, the accretion disk of matter falling to a star in the first place, because there's a continued rotation, it'll be a thin disk. It won't fall in from all angles. And not only can we observe that as it gets hot in the X-ray, we can also see other stars falling into the black holes. So there'll be a dark dot, and the stars will be falling into that, and we can measure that. Okay. So this could also indicate that the center of galaxies may be black holes. These may also be something called quasars. These two things may be the same. Some people think that a quasar is actually similar to a neutron star, but with respect to a black hole. So what we're seeing is light spraying out along the magnetic axis in a very, very, very bright and powerful form.